What's the evening mean? That scares me. What does that mean?
So she said she's still around for a while.
Oh, okay.
And
That's this afternoon.
okay. And so yeah.
There's a difference.
Okay. And then yeah, so that should be good. And she said that she'd send the one to the Texas and that needs to go.
Okay. And I need to talk to one person. Okay. Thank you. This never ends. Hey, good afternoon, good afternoon. This is going to be an awesome lecture. Now, I'm not saying that I'm going to do a good job. What I'm saying is the material we're covering is going to be really interesting, especially where you are right now. And so, first off, I totally understand why a lot of these seats are empty, and that's people making decisions, personal decisions about what's best for them. I want to applaud all of you who are in this room right now, because I think you made a really, really good choice. Interestingly enough, it's a very efficient choice because now you're going to experience this, and as you've already learned, and we all learned in COVID, experiencing this material live creates a much better chance for a longer-term memory than if you just watch it on a screen. So this was a very efficient use of your time because you're going to absorb more information. And I think you're going to find this, especially as you start thinking of the final, really important. So I'm really glad that you're here, and I appreciate that. We're going to start moving pretty quickly through material, and I'm hoping that through your preparation for the third midterm, you're getting to have all of these ideas and concepts coalesce into a pretty interesting picture of organic chemistry. And so we're really going to seize on that at the beginning of this lecture. So here's what we're going to talk about initially, is the epoxides. Interspersed today, I'm going to be throwing up some of what I consider to be some, I think, really interesting recent photos that I was able to take, just to get your mind set. So here is a great little thing. It's called a jeweled puffer sitting in it's called a pencil sea urchin in Hawaii. And just get your mind set because here we go. We're going to start with a flashback, and what I'm going to be doing is I'm going to be talking about epoxides, and we've already talked about this, but I'm going to refresh. And I'm going to refresh the epoxide story, and in particular, what I want to talk about is what happens when we take an epoxide, which is a three-membered ring with an oxygen in it. It's an ether, but it's a highly strained ring. What happens when we put a proton on that? And to have that conversation, I'm flashing back to something you're very familiar with, which is a three-membered ring intermediate of a halonium ion. And this is the flashback. And the big thing we talked about with the halonium ion was that when we have a choice, the water is going to attack the more highly substituted carbon because that highly substituted carbon, and the analogy here is to our protonated epoxide. The reason that we attack that is that when we look at the contributing structures of the halonium ion, we notice that the one on the right that has the majority of the positive charge sitting on the carbon that's most able to accept it because of hyperconjugation and the inductive effect, that's the major contributor to the contributing structures, so we get a structure such as that shown. And so when you realize that, you realize that if I'm a water molecule, as a water molecule, I'm going to attack the carbon that has the majority of positive charge. And to put that in perspective, here is the actual charge density. It's not even close. It's all blue over there. There's hardly any blue over here. So although at first you might be concerned about sterics, you've got steric hindrance from that methyl group that's going to prevent the water from attacking. No. The thing is sp2, it's planar, that methyl group is nicely out of the way. So the big story, and this is review, but the big story is we went Markovnikov with the water attacking because the water goes after the higher positive charge. That's the three-membered ring when it comes to a halonium ion. What we're really talking about is this group, which is an epoxide with a proton. But what I want you to see, there's nothing new here. Everything we just said is going to be absolutely transferable to protonated epoxides. So what I love about having this be the last couple of reactions we talk about is all I'm doing is drawing on your previous knowledge to present a brand new story, but you already know the answer. You already know how the story ends. Because when we think about the protonated epoxide, so we've got an epoxide and acid, when we think about that, what we realize is that, in fact, this is a minor contributor. That is the major contributor. For the exact same reason, we had the same story with the halonium ion. Because now, on the right here, we have these two carbon atoms which are providing hyperconjugation and inductive effect stabilization of that adjacent positive charge. That's going to be the most highly populated contributor. So even though it's a hybrid, that's the major contributor. In other words, same song, different verse. Identical story. As a result, it should not be a surprise if we protonate this epoxide. What we're going to get is we're going to get attack here on the more highly substituted side of the protonated epoxide. That is the side view of this structure. That is the bottom. So what we're looking at right here is where the water is going to attack. That's where the positive charge is. All of which is a redundant story. More methyl groups, more hyperconjugation, more sp2-like character, more inductive effect, more positive charge, bang, that's where it goes. Okay. So when we look at this, that's why we get that story. And so we went through this, and I'm going to pause here to let you fill in any details you didn't catch when we talked about this last time. So make sure you've got that filled in. But there's the story. It's literally same song, different verse. We got to that three-membered ring intermediate totally differently. We took an epoxide, we added some catalytic acid. But when you look at the personality of that three-membered ring, it's, oh, this is familiar. This is an old friend. I get this. And so if I'm in water, I know where water is going to attack. And we're going to do the same thing we did with the hydrohalogenation reaction. We're going to take the proton back off, done and done. And so we get the exact same story. The difference is, instead of getting a halohydrin, of bromine on one side or chlorine on one side and OH on the other, we're adding anti, once again, but now it's two OH groups at the end, so it's a vicinal diol. But it's got to be anti, because it's a three-membered ring. Again, same story. Same song, different verse. Okay. Unfortunately. And there's always an unfortunately. That's not the full story. This is what happens when we take a three-membered ring and we add acid along with water. But we can run this reaction a different way. We can run this reaction in base. In other words, water is not a strong enough nucleophile to attack the epoxide and open it up directly. That's why we had to add the acid catalysis. So the acid goes in and makes that a better leaving group. The OH is a better leaving group instead of just the epoxide opening. But if we use a much stronger nucleophile, we can hit that epoxide directly, and that's what we're going to do. So you finished writing this down? I don't want to rush. Okay, here we go. What we're going to do is now we're going to open this up, not in acid, but we're going to add a strong nucleophile. In particular, what we're going to add is OH minus. And OH minus is a nucleophile. This is an electrophile. Why? It's an electrophile because it wants to make a new bond. What does the epoxide, in terms of energy, what does the epoxide get back by reacting with a nucleophile? Why is that oxygen a good leaving group in that three-membered ring? Ordinarily, oxygen is not a great leaving group, but it is in this case. What's the story? Ring strain. There is a lot of strain built into that three-membered ring because the angles are not right. They're 60 degrees, not 109. That's a lot. So it is waiting for a suitable nucleophile to pop that thing open. So that's why we characterize it as an electrophile. OH minus is either a base or a nucleophile. It's clearly going to act as a nucleophile in this case. What's going to happen though? And here's the story. Based on what you know, there's no positive charge here. There's no contributing structures. What you see is what you get with that epoxide structure. Without the proton, no positive charge, no contributing structures, no distortion. So what do you know about a process where a nucleophile attacks an electrophile? We're not going to deprotonate anything because we only have carbon-hydrogen bonds. We're not deprotonating anything there. So what kind of mechanism are you thinking about? We're going to substitute. We're not going to eliminate. There's no way to make a double bond out of this thing. So what are we going to do? SN1, does that make any sense at all? No. So it's going to be SN2. What do you know about SN2? We've got two potential carbons that it's going to attack. One has two methyl groups, one doesn't. One has two hydrogens. Which side is it going to go after every time? Side with the hydrogens. Remember, primary reacts faster than secondary, and tertiaries don't work. Sterics, steric hindrance. So guess where this is going to go? This OH is going to go over, whoops. This OH is going to go over here, wham, to generate that intermediate. A perfect SN2 reaction. Well, what's going to happen now is we're going to take this proton and we're going to add it there. We're going to add, I phrased that poorly, we're going to add a proton there to generate our final product. So the big point, this attacks the C atom with less steric hindrance. And that's not news because, in fact, that's what SN2 reactions do. The nucleophiles hit the side with less steric hindrance predominantly. And this product is also a vicinal dihalide. Okay. I said it right, I just didn't spell it right. There we go. Now, I'm going to come back here, but I just wanted to point out, wait a minute, this is a vicinal dihalide. So, if we have two ways to get from the same starting material, namely epoxide, to vicinal dihalides, why have I told you two different versions? What do you notice that's going to rear its ugly head because of what I've just done? The nucleophile, water versus hydroxide, attack the different sites. What's that going to do? How is that going to make your lives more complicated? There's a single word. Starts with S. Stereochemistry. Ugh. Let's watch this. Just to make clear what we just talked about. No contributing structures. We are going to attack that site because there is less steric hindrance. And if you look, there's all the steric hindrance there it is. If you're a nucleophile, you're attacking that one every time. And just to make that point visual of why it attacked there. But what we're saying is, you do this with OH minus, you're attacking the less hindered site. You do it in acid with water, you attack the other carbon. As a result, we get a skull and crossbones. Watch this really carefully. In your mind's eye, you can tell what's going to happen here. I'm going to start with a single enantiomer. I'm going to start with this one enantiomer of the epoxide. So single enantiomer. I'm going to protonate, but the water, after I protonate, is going to attack that carbon from the bottom. I didn't really emphasize it because it's a three-membered ring. Just like with the halonium ion, we get a trans product. We get anti-addition. So I'm going to attack that more hindered side. And so let's draw that out. And what do we get? Attack from the bottom, as written. And that's ugly. Let me get that right. I don't like that. Need to put a little angle on that. Now I'm going through the step, I'm taking the proton away already. And that's what we're going to end up with. Do a quick stereochemistry check, that's R. Question? So, mechanism, so by the way, it's specific in all the directions. This should never be a question in your mind. Box problems, we don't require electrons. Mechanisms require all electrons, all charges. This is not a mechanism, I'm just doing a box problem. You'll notice in all my mechanisms, all electron pairs, all formal charges, everything, everything, everything. When it comes to just the box problems, I'm just trying to get across what the answer is. So I'm not really focused on format. Same with your box problems when I'm just talking about the reaction. Okay. Now, I think you know where this is headed. Same molecule, same enantiomer. Go ahead and write the product of reactant with OH minus. Who saw that coming? So notice, in both cases we get a vicinal diol, but starting with the same enantiomer, depending on which side attack, we get different enantiomer products. Yes? No, so it's diols. What did I say? Did I write dihalide? Oh my goodness. Hopefully I said it correctly, I just wrote it wrong. Look at that. Wow. Okay. Thank you. Problem solved. All right. Any questions about that? Pretty cool. All right, here we go. Do this one. In each case, the nucleophile has to attack from underneath. In the case of acid, we're going to attack the more highly substituted side. In the case of base, we're going to attack the less substituted side, but always from underneath. You always have to attack from underneath of this stereoisomer. It has to be opposite of where that oxygen is. So what that gives us once again, different enantiomers. Because we started with a single stereoisomer, we end up with a single stereoisomer. In both cases, we are anti, but we get enantiomers of each other. Really interesting. This combines so many different elements we have learned in this class into one situation. That's why I love ending with this. Okay. Any questions about those? All right, here we go. Grand finale. Fill those out. Ozzy Osbourne reaction. What are we going to get? Syn addition. Is that molecule chiral? Nope. There's a plane of symmetry right through the middle. Not chiral. On the other hand, first, if we add, notice the 3, we add the per acid, not the carboxylic acid, that creates what? When you see CH3CO3H, what is that going to create out of an alkene? Go back, the epoxide. Remember that bizarre mechanism with arrows going all over the place? That was that. So that makes the epoxide from that alkene. Now, we're going to add either acid or in water, or OH minus. And what we're going to generate is not syn addition. What is it? It's anti. Now, the epoxide can form on the top or bottom, so it turns out we're going to get, it doesn't matter now, acid or base, because in both cases, we're going to get both enantiomers in a racemic mixture. That's a tough one to see that you get the same place. You get to the same place. Because in this case, there's no differentiating between sides of where the carbons are. And we're not starting with a single enantiomer. The epoxide can form on the top or the bottom. We can attack either one. It's always anti. Those are your anti-products. That's what you're going to get. So not now, but on the final, you could imagine there's going to be synthesis questions where you're either going to have a cis vicinal diol or a trans vicinal diol, and you've got to distinguish between the two. And I'm just emphasizing, we did this already. That's a review. But I wanted it on one page to make that point. That there's so much going on here, it's so rich. But what I want to just keep saying over and over again, I haven't said anything new today. Everything we've talked about, you have seen before, just not in the context of epoxides. And that's what your second semester of organic chemistry is going to be like. Very few new ideas, but we're going to take a look at new situations, so different things you've learned are going to apply, but it's nothing new. This is where things are going to go, and it's really exciting. Because we're going to take this in so many powerful new directions. Okay. Are you ready for the absolute final reaction of the semester? Yeah. This is it. Ta-da! Now, taking this idea that you've already seen this before, there's nothing new here. Keep moving, there's nothing new here. Turns out alcohols and alkoxides, they react identical to protonated water and a hydroxide. So alcohol and acid, water plus acid. Same song, different verse, but now we've got an alkyl group hanging along instead of a proton. So we're not going to get a vicinal diol, we're going to get an alcohol with an ether. But it's the same story. So you've already seen this. Go ahead and write what's going to happen. So now, what you know is that this is going to be with base. That's analogous to OH minus. Therefore, this is an SN2 reaction, and it's going to react here from the bottom. So what we're going to get from the bottom now, we're going to get that ether. It's just like OH minus, but we have the alkyl group attached, so the alkyl group comes along for the ride, but nothing new here. But it's a new kind of functional group. Now go ahead, before I do it, go ahead and write the product of this last one. This is the last piece of chemistry we are going to do this semester. You'll see what we're going to do later. We're not just giving up, obviously. Okay, write this out. Show it to the people next to you till you all agree you get this right. I want everybody to get this right before I show you what the answer is. This is it. This is the moment. Okay. Here we go. Who got that right? Be proud. Hands up. Who got that right? I'm excited. That's a lot. That is a testament. If you got that right, a reaction you've never seen before, but you could do the analogy, you understand how it works, you were going through the mechanism, you had to figure out all the regiochemistry, all the stereochemistry, you got all of that right, you got the right answer, you have come a long way, and I'm very excited about that. That is awesome. Okay. That's it. We have finished the reactions that we are going to cover in OChem 1, which is why, oh, wait a minute. Oh. Hey, twin brother, is that you calling in? Wake up.
Absolutely. I wanted to tell your class about the key paradigm of organic chemistry. You know, the rule that makes the synthesis of complex molecules possible.
So what is the key paradigm of organic synthesis?
Well, the key paradigm of organic chemistry is this. Functional groups, like alcohols or alkenes, well, they react the same in complex molecules as they do in simple ones. You can look at even complex structures and figure out how they will behave in reactions by focusing on the functional groups. Got it? Functional groups react the same in complex molecules as they do in simple ones.
That's awesome and it makes so much sense. But hey, dude, I got to ask you this. You never seem to work. What do you do for a living?
Oh, me? I run a hedge fund. You know, foreign equities, alternatives, distressed real estate, the usual.
Okay, if you know that, is it true that in the future, investment funds will be run entirely by computer algorithms and AI instead of people?
Hey, bro, haven't you figured out that I am a computer algorithm? What? Peace out from here.
Okay. This is, in every way, by the way, I was serious about the computer algorithms running investment funds. So any business majors, sorry. Nevertheless, okay, victory lap. Here it is. The key paradigm of organic chemistry. The key paradigm. Functional groups, the chemistry you have been learning, and I, just for the sake of not turning this class into a writing marathon, use really simple molecules to demonstrate the reactions. But make no mistake, the reactions we learned on simple molecules work exactly the same in complex molecules. That is the key paradigm that makes organic chemistry a logical field. So what I'm going to show you in rapid fire, so I gave you the answers so you don't have to write anything here. I just want you to enjoy this literally. Take a look at that molecule on the left. That is a molecule that's on the way to manufacturing a really important pharmaceutical. Flonase, something you've probably seen. It treats asthma. Anyone with asthma knows Flonase. It's an awesome drug. So now I want you to look at that reaction and say, what could be going on? So you take a look at this molecule, you look at all of the different functional groups. And you're saying, okay, I've got this. How do I characterize that? Well, that is I minus. That is a nucleophile. So I'm scanning this structure to find what? Chemistry, you know. A leaving group. Who sees the leaving group in that molecule? What atom is it? Chlorine, 100%. Yeah, there's a whole bunch of stuff there. but it doesn't matter because this is my leaving group. And being that that's my leaving group, what I'm going to do is I'm going to, and you already have this, so there it is. You take iodide as the nucleophile, you react it, and what you end up with, sure enough, is an iodine there. You now know this chemistry. So this is the big thing. Obviously, we would not get very far if every time we were reacting a molecule, I made it this complicated so you were spending your entire time drawing. But make no mistake, the chemistry you're learning absolutely applies to these situations. So, let's go down here. This is a synthesis of Lipitor, one of the most commercially successful pharmaceuticals. Do you recognize that structure over the arrow? We did talk about it Monday. That's one of those sulfonyl chlorides. What is a sulfonyl chloride going to react with? What do the sulfonyl chlorides react with? The OH. Sure enough, ding. That reaction is worth billions of dollars, by the way. Okay? Paxil, a drug used to treat depression. We talked about this reaction. I didn't really focus on it. I talked about PBr3, and I just mentioned that SOCl2 works as well. We can't do the mechanism of SOCl2 because it has a little trick in it that we're not ready for, but we're going to see SOCl2 next semester, and so you will learn that before we're done. But SOCl2 also reacts with what? Alcohols. So sure enough, what we're going to do is we're going to replace that with this. Now, you take a look at this situation, it turns out this reaction is going to take place. It's an alcohol, and we've got what kind of haloalkane is that? It's primary. A primary haloalkane reacts with an alcohol as a nucleophile by what mechanism? Primary haloalkane, any of the nucleophiles, how does it react? Bang. There it is. Okay. That's so much fun, we're going to do a couple more. Oh, you've seen this one. This was hanging out at the bottom of our table of nucleophiles. What does that reagent do? By the way, these are all from commercial syntheses. These are actually used to make these pharmaceuticals, these reactions that you now know. So what does that always do? E2. So what we're going to do is we're going to look here and say, aha, do we have the right geometry for an E2 reaction? Why? Because it is exactly, with a little more enthusiasm next time, but that's okay. That's okay. There we are. Oh, have you seen this before? What do we notice in this thing? A terminal alkyne, and what is that going to do? It takes off the H, so what is going to happen here? And which side is it going to react in? It's SN2, Br, because Br is a better. Look at this. Dang. But chlorine is still a leaving group, so we're going to add this. I'm going to have more to say about that in about 2 minutes. We're going to add that. That is a nucleophile, Cn minus. It's on your table. I'm going to say more about that one, actually. So now we're going to get another SN2 reaction. Bang. There we are. Okay. Oops. I don't know why that disappeared. I forgot to do that one. Whoops, my bad. I skipped it. That is a leaving group. So this, as a nucleophile, reacts. The leaving group goes away, and that's our product. Sorry, I missed that one. I was so excited to go down to the Paxil. So there we are. Those are the drugs that we just showed you. The chemistry that you've been learning in this class is relevant to those cases. And it's because of the key paradigm in organic synthesis, which says a reaction that we've been talking about on a simple molecule, it works exactly the same on a complicated molecule. And that's what organic chemistry is all about. That's why what we're teaching is actually highly valuable. I just don't pull out complicated structures like that because literally it takes too long and there's too many ways you can make mistakes that aren't relevant to the chemistry. What do you think about that? If the very first day of class I showed you that and said you're going to look at that and go, yeah, okay, I got that. Wouldn't you be impressed with yourself? Because I'm impressed with you. And here's what I want to say on behalf of all chemists. Who understood what we just did? Be proud. All I can say is welcome to my world. And I'm serious about that. Because there is an entire world that's built around these kind of things in pharmaceuticals which have absolutely transformed medicine into what it is today. But very few people on the planet understand how it works. You're now in that community. So it's a technology that is owned by the very few, but it's one that has helped humanity in ways that you can't even calculate the number of times and number of ways it's helped you personally, as well as everybody who has access to healthcare. So this is important to me, and I hope that you see how what we've been doing is so incredibly relevant. But now you are among the few. And it's going to get better, because we're going to learn a whole lot more cool stuff next semester. But it's going to get better. Okay. Here we go. You will learn how to analyze a complex... you look at a molecule and accurately predict which atoms will react to make new bonds and which will break during reactions. You've been doing that the whole time, but I'm going to declare victory today. And you will learn how to analyze a complex molecule structure so that you can predict ways to make it via multiple reaction synthesis. You did the homework. I'm going to declare victory today. That's an ongoing process, I understand, but I'm going to put that down. We're getting there. Now let me set a timeout real quick. That homework was challenging, but it was not a distraction. It was actually the best tool I've ever seen to help you prepare for the exam on Thursday. Why? Not because it's going to be 7 complicated synthesis problems and that's all it is. No. And I want you to take this to heart. It's because the process of trying to figure out how to get the reactions to fit together to make the product molecules was using the information that you'd been learning. Using that information is the best way to set a long-term memory about that information. It was actually a learning device. And so struggling through those syntheses, even if you didn't get them right, meant you were going through in a very time-efficient way to understand how to use the material. So I want to tell you, and I want to hear your feedback on this after the exam, but we did that as a learning device. And I think it's been validated by a lot of neuroscience that that's how you create a long-term memory, is use the material. Don't just read it. Don't just review it. So that was the goal. Nevertheless, that is the key idea behind organic chemistry. All right. I did some retrospective thinking, and I'm going to do this quickly. I have a couple of points I want to make that I think I didn't make well. It's relevant to the exam, but it's not really exam material. But it's things that, before I stop this, I just want to say. Good leaving group leaves to create a stable anion or molecule. So this is something you've seen before. For example, Br- is a great leaving group But we also saw several examples where H2O was created. That was the leaving group. Nucleophiles, so that's easy to explain, what a good leaving group is. Nucleophiles is not. I kind of dodged this. And as you've been studying this material, you were probably thinking, he uses that word a lot. I see there's a table of them. What are they? How do you define a good nucleophile? And it turns out this isn't easy. You look at the table for reference, and here's what you know. Halogens, in other words, Cl minus, especially Br minus and I minus, are both good leaving groups and good nucleophiles. They're the exceptions. They are the very rare exceptions. Most nucleophiles are not good leaving groups. I never said this out loud, and I want to say it out loud. In the case of the halogens, they're both. They're both nucleophiles and leaving groups. But the rest of the groups in that nucleophile table are not good leaving groups at all. There are exceptions. There's the water. There's the ones at the bottom, but the vast majority are not. I dodged this. I never said this out loud. And so I just want to make this point. It's a little point, but I just want to make this point. I find it's best to mention it after you've gone through the process of being familiar with the material. If I say it at the same time, I don't think it works. So I've given you this, and what I wanted to point out was that you might see this written as Na plus, Cn minus. You might see it written as K plus, Cn minus, or you might just see NaCN, NaCN, or KCN. All of this means the same thing. The Br minus, I minus, and you can put chloride in there as well if you want. They're the exception. They're good leaving groups and strong nucleophiles. Usually, the two don't go together. Again, I'm saying this because I just never said it before. And I just want to make that clear. What defines a good nucleophile means it's going to make a strong bond. It's kind of hard to predict. That's why we put them in a table for you. A good leaving group means it's going to be a stable anion or it's going to be a stable molecule. That's what makes a good leaving group. And as we're going to see next semester, Cn minus, I'm calling it out. You saw it in the examples that are used in industry. It's a good molecule. It's a good nucleophile. We don't use it first semester. You're going to use it a lot second semester as a nucleophile. So I'm just calling it out. I just want to put a little note in your mind. So when I come back to this moment and I say, your future self, after we win the national championship and have the celebration parade and all of that kind of thing, we're going to come back and be in the same room. And I'm going to say, remember when we said Cn minus was a great nucleophile? You're going to say, yeah, that was before we won the national championship and had a nice parade. But I remember that now. Okay. If we can beat it now. But now, here we go. So these are strong nucleophiles and good leaving groups. That makes them kind of unique. All right. I want to clear your minds. We are done with the chemistry in this class. Period. End of story. Done, 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 done. We're going to do something ultra cool, but before that, I want to clear your mind. So there is absolutely no point to what I'm about to show you, but I want you to clear your mind. I want you just to enjoy the moment, clear your mind. Aw. Hi. Okay. Ooh. I need a toothbrush. Wait. Is that a fish? Yeah, it's a fish. It's a good thing it's on yellow coral. It's called a bandit. My favorite picture of all time. There it is. My favorite fish with a perfect background. Here we go. Mind clear. We're entering a new world. I'm about to, for the last amount of time we have today, but all the rest of the semester, we are totally switching. This is on purpose. I'm doing this now so as you prepare for the final, there's no new chemistry. You're going to be able to crush the final. Even if there's still some soft spots coming into the third midterm, you're going to get that information. You're going to have time. All we're going to do is help you master whatever is not there already for the final chemistry. But now what I want to talk about is something that I have a feeling in a moment of despair and being overwhelmed, you lashed out and you said, wait a minute, how do they know any of this? Are they making this crap up? And that's a fair question. So when I say the product of a reaction is the product of a reaction, how the blank do we know that? I'm about to show you. There's a technique that we use to identify chemical structures. So we can take a sample of a molecule, put it in solvent, put it in a machine, get a readout of that machine, and assign the three-dimensional structure of that molecule. And that's what we do for a living. This department has about 5 of these machines, and all of the graduate students will look at these results from this analysis multiple times a day to verify that what we're doing is what we say we're doing and what we thought we were doing. Or it might be a surprise, but we can identify molecular structure. So that's what we're switching to. And so it's a technique that unfortunately is heavily dependent on physics. So instead of turning this into a physics class, we're just going to summarize physics. So here we go. This is the new handout. And this is, if you haven't downloaded it, this is the bonus to download. Part of it was what we just did, the stuff I wish I had said. But here it is. What we're going to be talking about is NMR. What does that stand for? Nuclear, magnetic, resonance. Are you kidding me? Yes. Everything about that is quantum mechanical. Can't avoid it. Got to talk about the physics. So we're going to do this without equations, even though there's equations, of course, that underlie everything I'm about to say. And I am just presenting these to you, and we're just going to take them as fact. In your physics classes, you're going to dive into this stuff. But as far as we need, you just have to accept certain things. For example, moving charge generates a magnetic field. Who knew that? Awesome. Who did not know that? That's how electromagnets work. If you put electricity in a coil of wire, that will create a magnetic field. That's an electromagnet. So moving charge, like electrons, creates a magnetic field. We don't know why, but it just does. And you can measure it, and you can quantify it, and you have equations that describe it. But if charges move, they create a magnetic field. You just got to trust me on that. And a moving magnetic field causes charges to move. What? Bet you didn't know that. Who knew that? Cool. These are described. If you want to dive into it, by Maxwell's equations. It's all quantified. That ladder, by the way, that's how power is generated. Do you ever worry about that? Say, wait a minute, I put coal or natural gas into a power plant and I get electricity out? What? I haven't seen electricity come out of my car. What are we talking about here? It's because what it does is it creates a magnet that moves, and that magnet that moves, that's what the fuel is used to do, is to turn the magnet, and by turning the magnet, you induce electricity. That's how it's a power generation. So this thing right here, that's how we make all electricity. Question? Besides solar. Yes?
Do MRIs work by...
MRIs later. We're getting to MRI. All right. Sorry, but you'll see. You'll see. That's not a detail. We're getting there. Atomic nuclei, like electrons, have a quantum mechanical property called spin. What? Who's heard of spin? Who knows what it is? Can you describe it? Yes, what's spin? I can't either. So we're even. But it's a thing. Exactly. But I don't know what it means. I mean, are electrons spinning? Actually, no.
I thought the name spin was just from the origin of the word.
Yep. Spin can be thought of as a small magnetic field around the nucleus created as if the charge of the nucleus were circulating. Do you notice the big words here? As if. I'm faking it. But that's the way to think about it. So here's the story. Am I talking about electrons there? Am I talking about electrons there? No, that's the big story. Nuclei. Nuclei of atoms. They have, what's the charged particle in a nucleus? Proton. Therefore, when you think of spin, you need to think of as if it had a magnetic field, as if the nucleus was spinning and the protons were spinning. Moving charge creates magnetic field. Do you see the connection there? You probably didn't know this, but that's what spin is. It's a small magnetic field associated with the nucleus that can be calculated. I'm not saying this is what's happening, but it can be calculated as if the nucleus was spinning, and therefore the protons inside the charge were spinning as well. Spinning charge, moving charge, magnetic field. You get a little magnetic field associated with the nucleus. You just got to accept it. And frankly, we don't understand why this happens, but we can quantify it. And it's been verified by every experiment that's looked at it. Okay. Nuclear magnetic resonance is used to assign structures of organic molecules. We care about, and in this class right now, we care about hydrogen, the most common isotope of hydrogen. In NMR in general, I'm going to mention this now and then we're going to forget about it. We also care about a rare but present isotope of carbon. Carbon is mostly 12. 13 carbon has an extra neutron. That actually occurs a lot. Everything I'm about to say about hydrogens also applies to C13. We're just not going to talk about it in this class. I just wanted to say, hey, this works for that too. In this building, all of our graduate students, all the TAs, they use C13 and hydrogen. In this class, we're only going to use hydrogen. Got to keep it simple. Okay. All right. This is the big one. Nuclei with spin quantum number 1/2. That is what those have. What does this mean? Remember, in Gen Chem, you learned all these quantum numbers. And you memorized the pattern, you took a test on it, and of course you probably, if you're like me, had no idea what you were doing, but you memorized, yeah, okay. It turns out that that has to do with the magnitude of the magnetic field associated with the nuclear spin. So when we say it's spin 1/2, that characterizes it. There's no analogy to anything in the physical world I can point to. It's not like a tiny little magnet on your refrigerator. No, it's not. It's not like anything. But you have to remember that these are quantum mechanical properties, and a nucleus can have different spin quantum numbers. We care about spin quantum number 1/2. It turns out that the proton, the hydrogen at nucleus, and C13 have spin quantum numbers 1/2. Other types of nuclei can have spin quantum numbers of 1, 1.5, so on and so forth. Not relevant to our story. We only care about hydrogens because they're spin quantum number 1/2. What does that really mean? It means it has two possible states. it has one state, which is the plus 1/2, which is the lower energy, or it has minus 1/2, which is higher energy. You're used to this with electrons because you can think about flipping spins. That's what we're talking about. So, no electrons now. Nucleus, hydrogen nucleus, has a spin quantum number of 1/2, which means it has two possible states it can exist. Plus 1/2, lower energy, minus 1/2, higher energy. But wait a minute. In the absence of something special, the energies of plus 1/2 and minus 1/2 are the same, and it's totally irrelevant to us. But if you add a magnetic field, super strong, by the way, super strong magnetic field, the plus 1/2 spins, because remember, spin is a magnetic field. It will interact with that external magnetic field in the room, so the plus 1/2 is lower energy than minus 1/2. Are you with me? So we've taken you through this progression of ideas. It culminates in this story, that a nucleus of a hydrogen atom is going to have a spin quantum number of plus 1/2 or minus 1/2. And if you put nuclei, hydrogen nuclei, in a very strong magnetic field, the plus 1/2 nuclei are going to be lower energy than the minus 1/2 nuclei. I know this is kind of a weird picture because, of course, you're saying, wait, I thought we were talking about molecular structure. We are totally getting there. All right. If any of that is unclear, this is the key statement. The difference in energy between the plus 1/2 and minus 1/2, there's our spin plus 1/2, there's our spin minus 1/2, is proportional to the strength of the magnetic field felt by the nucleus. Stronger magnetic field, bigger difference in energy. Because remember, what I want you to think about is nuclear spin translates to a little magnetic field on the nucleus. So it's going to interact with other magnetic fields that we add in the laboratory. So this laboratory magnetic field is what I'm talking about. We put the sample in a strong, super strong magnet. And when we do that, the spins line up, plus 1/2, minus 1/2. We'll talk about how they get to each state in a second. Okay, are you kind of with me what I'm doing? If not, ask me a question. Because it's still abstract. Let's get closer to where we need to go. Oh. Uh-oh. Uh-oh. Oops. Okay. Electron density in a molecule, oops, electrons have charge. So if we stick a molecule with electron density in a magnetic field, what's that going to cause the electron density to do? If we've got a magnetic field and we've got electron density, the electrons have a charge, negative charge, but they have a charge. What are they going to be induced to do? They're going to move. And they're going to move in a characteristic way. Moving charge creates a magnetic field. Magnetic field creates moving charge. And when they move, you've got, think about this. This is this weird sort of cause and effect thing, tail, dog, wagging, whatever. So you induce the electron density to move, but what does that make? A magnetic field. And it turns out it goes in the opposite direction. This thing has directionality. It's called the right-hand rule. You'll really enjoy that in physics. I say that sarcastically. That's why I'm a chemist. Maybe you'll love physics. I don't know. So here's the weirdness. You've got a nucleus. It's under electron density. We put the whole thing in a magnetic field. The nuclei line up, opposed and against the magnetic field, the spin. But now you've got electron density on the outside of the molecule that is circulating, creating its own magnetic field that literally fights the external magnetic field, but the nucleus is underneath. That's the picture. Sounds like total chaos, doesn't it? Turns out it's super incredibly useful and interesting. Why? Here's the experiment. In the classic experiment, the molecule of interest is placed in solvent, by the way, we replace the hydrogen atoms of the solvent with deuterium. Deuterium. Therefore, they're not hydrogen atoms, therefore they don't interfere. You then put the spinning tube in a very strong magnetic field. The sample is exposed to radio frequency irradiation. What? You turn a radio on? Play music? What the heck is going on here? And if it is of exactly the right frequency, energy is absorbed and the spins flip from plus 1/2 to minus 1/2. They come into resonance. The absorbed energy is plotted in the spectra. Okay. Holy cow. We're going to get back to this. What are we talking about? Here's the experiment. We place the molecule in solvent in a strong magnetic field. This is the experiment. What that does is it means your spins are going to line up. Plus 1/2 is going to be lower in energy. Now that it's in a strong magnetic field. We then throw in energy of exactly the right energy level, in other words, frequency. We shoot it in. It happens to be radio frequency waves. Oh, I should be more creative than that. Here we go. Pow. So this is electromagnetic energy. And it happens to be radio frequency is what happens to work. But it's electromagnetic energy. That energy is absorbed by the nucleus and it flips. Okay? This is sounding weird, but this is what happens. So then, what do? The energy absorption, nuclear spin flipping phenomenon is called resonance. So the plus 1/2 spin state hydrogen nuclei absorb the energy, flips its spin. That's called coming into resonance with the energy. So now you understand this experiment. Nuclear, magnetic, resonance. So what you should be thinking is, okay, I have somehow woken up in a physics nightmare, and we're talking about quantum mechanical effects and strong magnetic fields and absorption of electromagnetic radiation. Please get me out of here. Wake up, wake up. No, you can't wake up. Because how am I going to connect that to molecular structure? Does anybody have any idea? I've given you the answer. I threw it in there. How are we going to connect that to molecular structure? The electrons. Most important question in chemistry. Where are the electrons? So what we can do is realize that the electrons that are floating around a nucleus that are circulating, if there's more electrons, their magnetic field fights the external magnetic field more. If there's more electron density, okay, I said that wrong. Let me get this right. If there's more electron density, there's more electron density circulating. The magnetic field it produces, which opposes the outside one, is greater. If there's less electron density, the amount of magnetic field is proportionately smaller. let's get back to what I said was the key to the whole frickin' thing, is this statement right here. Proportional. That means the energy difference between the nuclei under high electron density is feeling a net magnetic field that's different for the different nuclei, hydrogen nuclei in the molecule. So if we know where electrons are, we can predict where the different hydrogens are going to come into resonance. Therein lies the fundamental principle. So, key point. The energy of the electromagnetic energy that is absorbed must match exactly the energy difference between the plus 1/2, oh, that's a mess, the plus 1/2 and minus 1/2 nuclear now, spin states for resonance to happen. We monitor the energy that is absorbed by the nucleus as they are flipped. We shoot electromagnetic energy in. If it's absorbed, it doesn't come out. So we look at what goes in versus what comes out. And if something's missing, it was absorbed. We then plot that versus frequency. So we can measure the different places in energy where the spins flip. That's what we're doing. That's the NMR experiment. Okay. It's the last thing we're going to do. We've already said this, but I'm going to write it down, and this is all we're going to do today. The external magnetic field induces electron density to circulate, which creates its own magnetic field that, because of the way the physics works, will always oppose directly the external magnetic field. So, final statement, if you are a nucleus, there's an external magnetic field, think of it as a vector. You're going to have shielding from your electron density that operates in the opposite direction. The net is what you feel. That's in the laboratory. That's caused by the electrons around a nucleus. That's what you feel. And what we're going to learn is different kinds of hydrogens and molecules feel different fields. Therefore, they absorb energy at different frequencies. We measure the frequency. We can predict the structure because we know the most important question in chemistry, which is, therefore, we can predict what happens. Very best of luck on the exam. At 5 o'clock, I'll be in my normal office hour to answer any last-minute questions. Please trust yourself. I think you're going to do really well on this midterm.